after a few words. Okay, so
That's great. Yep. Yeah, that should be fine.
Got to click on
Yep.
it. All right, guys. So welcome to the third day of the AM, and today we're going to start with the first keynote, which is Professor Marcel Jackson from La Trobe University in Melbourne. And Marcel is going to be talking to us about algebraic advantages in machine learning. So please, Marcel, take it away.
Thank you, Guillermo. Apologies in advance because I meant this to be slightly more logic-y, but it's a little bit more algebra-y than perhaps I had in mind. But I hope to have aimed it at a reasonably accessible level so that maybe it will just count as a general interest talk anyway. So I thought I should start with some caveats. So it's not really machine learning, it's algebraic machine learning, which is a different thing, which is the point of the talk. And it's not my idea really either. So I thought I would start actually with a bit of a sort of a history of life on Earth, but I thought I should put a caveat on here. I don't know if you know this TV show, but if you do know the TV show, this is just getting close to what I'll be doing. So Philomena Kunk knows absolutely nothing about anything, but that won't stop her attempting to present a groundbreaking documentary about it. So I'm not an expert in the history of life or anything like that, but I thought it's an interesting perspective on machine learning. And I'm not an expert on machine learning either. In fact, I know very little. So that's why I should put up this caveat to start. So I do know a little bit about molecular biology because my partner works in this area in mathematical biology, modeling these things, and I've got involved with a number of projects now. And it is just remarkable how complicated the actual mechanisms of life really are. It's really astounding. And I thought it's kind of interesting to look over the history because it's quite a long history. In fact, it's quite strange that life emerged really quite quickly on planet Earth. This graph that I drew doesn't go back to the start of planet Earth, but it's only just slightly off the left. It's like 4.5 billion years. And as far as we know, it's not completely sure, but the earliest possible life that I think could have occurred is a little bit before 4 billion years ago. And the stromatolites in Western Australia are one of the earliest, more clearly verifiable proof of life, which are about 3.6 billion years ago. But nothing much happened for a very long time. I mean, when I say nothing much happened, the picture I just showed before, which was supposed to be some sort of DNA unraveling, that kind of thing did happen. And that is pretty incredible. And so no doubt it took a long time. Of course, it's hard for us to comprehend these timescales, since if you try and put hominoids on there, so human-like things, which have been around for maybe a couple of million, Homo sapiens maybe only 300,000 or 400,000 years, but then they're less than a pixel width on this, so you can't really draw it. But anyway, what happens was things started to get more complex. Eukaryotes, that's the ones where some cells engulfed other ones to make mitochondria and things inside, and you get cells with more complex internal structures. And eventually that led to multicellular organisms, which is clearly quite a big rise in complexity. But at least when it comes to diversity, so maybe I should have put complexity/diversity, there was this event around 500,000 years ago where sort of everything just reached a critical mass. So firstly, the eukaryotic cells which had enabled the multicellular organisms were primed, ready to become more complicated, but the conditions became right. So the oxygen levels that had gradually been building up since the origins of photosynthesis reached levels where this kind of thing was more viable. And there's this event called the Cambrian explosion. This graph isn't very accurate because there was also a big extinction after that, not the dinosaur one, a different one. And things just went pretty crazy then. And it actually happens really quickly in this time scale. Like it's suddenly just like, and here we are now. By the way, yeah, so in this, anyway. So I wanted to imagine though, what happens if, and this is possibly going to happen at some stage, some people would believe that it's already happened. What happens if we discover life from outer space? I mean, now, in all likelihood, it's probably not going to be these kinds of things that we see in the movies, but acknowledging that some people believe they've seen such things, I don't know. What's more likely is it'll be some sort of bacteria-like thing. I mean, already we know that these ones on Earth can survive in outer space. So it's like more likely the kind of thing will be floating around. And you'll notice I adjusted the color of the main part of the graph as well, because I could just imagine that someone would like start inserting alien genes inside human genes or something and would all get mixed in. But it would be more likely something relatively simple. But that would be one of the most fascinating things in the entire human history to have been discovered. And I'm sure that there'll be a scientific flurry of excitement trying to work out what these mechanisms are. I mean, it'd be a really amazing thing. So I wanted to compare this to the timeline of machine learning, which doesn't go back quite as far, but it seems like neural structures started to emerge in the late 1940s. Of course, computers have only been around for a few nanoseconds at this point. The word machine learning first appears apparently about 1959. And there was a sort of fairly slow progress, partly because computers weren't very good. But really, perhaps they could have been a little bit better had people cottoned onto the right ideas. So backpropagation, which is a key feature of modern machine learning in its current form, was invented in the early 1980s, but it didn't necessarily convince people as a viable mechanism. Again, perhaps because computers weren't good enough. Of course, through the 1990s, computers did become a lot better. But what really changed things was the graphic processing units for computer games, which totally exploded this field. And they came into existence in around 2007, 2008. And the real excitement in the AI area was around 2010. That's only 15 years. And it is amazing to think how pervasive AI and machine learning is just in the media, in our lives everywhere already. When I remember going to talks in about 2012 or something, and they were saying, they can classify cats. You know, you can get pictures on the internet. It will tell you if it's a cat. I mean, this doesn't seem all that impressive now when you can just ask it to draw a cat and it will do a good job of it. When I say it, again, just like in life, it's not just that machine learning became the backbone of very advanced artificial intelligence. And I'm not saying that it is intelligent. I'm not suggesting that somehow these things are alive. I'm just using the word artificial intelligence as it's usually used to mean the stuff we're talking about. But it became very diverse. So we have large language models and all kinds of different versions of how these neural network-based machine learning would occur. So what would happen if we discovered some sort of machine learning from outer space? You'd think there'd be some sort of flurry of excitement to try and work out what is this alternative. Now, it's a bit unfair because along the way, through this AI winter, there were other approaches to artificial intelligence, lots of them, and perhaps they just didn't really catch on, or because they didn't have the same potential. But actually, there is this interesting one, I think it's interesting, algebraic machine learning, which was invented about 2017, and it is completely different, although it does have some similar capabilities. And in fact, as a classifier, the inventors claim that it's actually a little bit better than traditional methods. And it has some other advantages. So it's somewhere between a machine learning and a sort of a constraint language, so that you can actually define problems without any training at all, and it will just attempt to solve them. So if you know some sort of logical basis for the structure of a problem, you can just encode that directly. But also arguably has the potential to be slightly more explainable because you can write down algebraically what it's actually doing to classify at the end of it, rather than just have some giant network of parameters. It's actually completely non-numerical, which is perhaps a slight hindrance, but they have found some clever ways to get around this and can deal with numerical data quite satisfactorily. So this talk is about algebraic machine learning. So this is, it emerged from this, oh, it's got a spelling mistake. This should be Champlemont Centre for the, should be CH at the start for the unknown. This is a $500 million euro bequest by the Champlemont family, which were a cement family in Portugal. It's really a medical research company, but it's quite a big, not a company, research institute, but it's quite big, and there's a lot of computing prowess there and some mathematical biologists as well, and this idea has emerged from that. So as far as I know, the inventor is Fernando Martin Morato, who is more of a, I guess, computing, but does have a bit of a mathematics background at some stage of his training. And they've gone out of their way to quite significant extent, I would say, to try and get people involved in this. So they've given numerous talks. So this is one that I saw. There was actually a whole 2-hour workshop on this exact topic at this conference in celebration of Peter Cameron. If you don't know Peter Cameron, I think we've got a talk on the ligomorphic groups tomorrow, and this was some ideas due to Peter Cameron. So anyway, he's up at the front there. There's me. So I attended this talk. I tried very hard to work out what they're doing. It's actually the second time I've done this. I was unable to. I feel like, yeah, anyway. But at the encouragement of others, I've been meeting with them since then to try and decipher what they're actually doing. And this talk is really the result of those discussions, because I think what they're doing, regardless of whether it's actually a really great idea, it's at least a really nice idea. And it's a wonderful application of part of mathematics that's at least algebraic logic aligned, I guess. It's sort of universal algebraic. And so I think it's actually really worthwhile knowing more about. And it brings around a lot of mathematical and I guess logic-related questions as well, I think. So I don't know if it's actually a really great idea, if it will ever get its own Cambrian explosion, but it might do. So here's an overview of how the idea works. And the rest of the talk will be trying to give a better basis for this. And we won't see actually that much actual machine learning, mostly because, as I said, I'm not an expert in this. I'm really an algebraist, I guess. And so this is more about how it works more than it actually working. So information and data are presented order theoretically, and these are going to be recorded in a semilattice. I'll explain all these terms. But the idea is that as you get more information, you are collapsing down a semilattice. But all of this state of knowledge, so I think of this as like a knowledge space, is actually understood by way of the dual. And there's a duality for semilattices, which I'll talk about. But a nice way to think about this is in terms of the Fourier transform. So the Fourier transform is also by way of a duality. So you have a function, and then you look in the dual space, I guess the frequency space, and it's completely transformed into a different object. It's just as a sum of its, or just represents the frequencies that are required to build up that function. And there is a theorem, the Fourier inverse theorem or something like this, which is exactly an instance of, a specific instance of what's called Pontryagin duality that can take that function back to the original. Okay, so when we look at items 1 and 2 here, where I'm saying that the semilattice has been collapsed, this is a bit like what we're looking at is, if you like, simplifying the frequencies in the Fourier transform of a function. And you can imagine that if we were trying to simplify a function, we could look at its Fourier transform and see, oh, these are really dominant frequencies. We'll chuck out all the rest, and we get something that sounds pretty much the same. And in fact, this is done very commonly in sort of cleaning up noise in signal processing and things. So it's that kind of idea. And the fact that it is a duality sort of makes this analogy concrete. So I should say part of the reason I alluded to this, part of the reason that I think it's been hard to follow what they're doing is not because it's that hard, and I hope you will come away with a good idea about how it all works. It's just that they kind of invented a lot of some interest. They weren't aware of semilattice duality, and so they've sort of rediscovered it and invented a weird sort of amalgam of this as a sort of a new kind of mathematical object. And it's always hard to learn something completely new where there's no textbook, and where your only way of learning it is by attending a seminar and listening to someone explain it, and that's it. And some of their terminology is not, I think, perhaps optimal, but anyway, hopefully this new framework will be a better way to do it. Okay, so I promised I'd make this accessible, so I am going to just even explain an order relation. Probably everyone knows what an order relation is anyway. So just a reflexive, anti-symmetric and transitive relation. So we have reflexivity, anti-symmetry. If x is below y below x, then they have to be equal. And transitivity, I think, is probably very familiar. We can draw these by way of a diagram, sometimes called a Hasse diagram, where we just go upwards. So here A is less than or equal to E, A is less than or equal to G. So transitivity means we can skip upwards along these edges. Can't go sideways or downwards. Downwards is going, well, that'd be the other way around in the order. Less than or equal to means going upwards. So we have upper bounds. These are just the elements that are above a point. And we have possibly have least upper bounds, or we possibly don't. So here are the things that are above both A and B, and it's D, E, and G, and you'll see there's no minimum in this little set, D, E, and G. So there's no least upper bound for A and B. But if we look at B and C, we'll see that F is the least upper bound. If we look at the things above both B and C, then it's only F and G, and F is the smallest of them. And you can also get lower bounds, which I'll skip over. It's just the same kind of thing. These are just drawing. It's just like a graph. You can move them around. It's not the actual object. It's just a drawing. This is not a pipe, that kind of thing. Okay, so a joined semilattice is the basic algebraic object. Of course, these kind of things appear very frequently in algebraic logic, for example. So it's just an ordered set where pairwise supremums exist. And I'm just going to write plus, but you could write join as well, like the V symbol. I'll write plus. So the picture we just had wasn't a joined semilattice because we saw A and B had no least upper bound. So not a semilattice, it had to have a least upper bound for every pair. Now, of course, we also are interested often in least upper bounds of actual sets, which could be infinite. There's no reason why this has to be finite. I think for the basic understanding of algebraic machine learning, it's probably better just to look at finite semilattices because information ultimately is finite. Actually, the Algebraic AI company, which is the company that has been funded quite generously so far in the European funding rounds to explore this, they're very interested in the infinite case, just because in theory, they're kind of using this to model floating point arithmetic and things like this. And so they're quite interested to understand a more general framework where things are infinite. And then you might want infinite supremums as well. Or I mean, you might want to handle some cases where it's true and some cases where it isn't. So that one wasn't semilattice, but this one, which I'll use as my basic semilattice for exploring purposes, is a semilattice. So we can check, but this semilattice as an algebraic object, if we think of supremum writing it as plus, is generated by the points A, B, C, and D. So you can get this B plus C point. That's just the join or the least upper bound of B and C. A plus B is the join of A and B. You will see that B plus C is also the least upper bound of B and D. So in other words, B plus C is equal to B plus D in this case. They're the same value, but it's okay. So we have some generators for this semilattice, and I'm counting 0 as being given for free. So it's like a constant. And that's not really very important, but it's, I think, a cleaner framework for this. So I'll skip over this as well, but we can start completely algebraically. It's just a semigroup, so an associative binary operation that happens to be commutative and idempotent. And then you can recover order by defining x less than or equal to y if x plus y is equal to y. So I've skipped over this fairly quickly because I suspect it's probably very familiar to most people. But if it's not familiar to you, then I hope that it was of some value to have at least skipped over it a little bit. Suffices just to look at these pictures and understand that plus is the least upper bound in terms of going upwards. So sub-semilattices, we'll need these. These are, of course, that's what they should be. It's just a subset that's closed under the sum. So here we go. These blue dots are an example of a sub-semilattice. 0 plus anything is just that anything, so that's fine. And A plus B plus D is A plus B plus C in this picture. So it's also A plus B plus D, by the way. I've just used A plus B plus C as the name. So this is closed under the plus of the original, so it is a sub-semilattice, and it looks like this. Homomorphisms, we'll need them as well. Of course, we can all make up what these should be. They're just like linear maps, essentially, but it's even easier than that because there's no constants, or if there are, it's just 0 and 1, I guess. So things are either there or not. So the image of a sum is the sum of the images. And these preserve orders. Perhaps I'll skip over the proof because I know I'll run out of time later, but you can think about this proof. It's a lovely little trivial, easy example of a proof that you could teach to a first encounter of algebra and orders in undergraduate, for example, as an exercise perhaps. So what I wanted to focus on a little bit was quotients. So as you would probably know, especially if you've done any algebra or universal algebra in particular, congruences are just collapses of things. So they're equivalence relations on an object that somehow preserve respect the structure. So in this case, our structure is just the plus. We could have asked for order as well, but plus defines the order, so it suffices just to look at plus. And it's just the idea that if two things are equivalent, then adding some other Z to those two things should also be equivalent. That's all it should mean. I've got some pictures to understand this. Okay, so just at the bottom here, I've got a reminder of that. And I'll just imagine I want to collapse these 2 points here. So that was A plus B collapsing to A plus B plus C. I'll need to check that if I added anything further to those 2 points, that they were also collapsed. But you can see that adding anything to this one either does nothing to it, in which case it's already been collapsed, or it gets you to the top, which was the thing it was being collapsed to. So this one actually already satisfies that property. So technically all of the other little dots should have a little circle around them because but in terms of what's actually being collapsed, it's these two. So the quotient of that semilattice looks like the one on the right. And it also gives a good example of a homomorphism. You just map things across in the obvious way with the two points that I've collapsed mapping to the top. So let's look at this one. If I was to collapse B and B plus C, now I need to check something more because there is something I can add to B and B plus C that isn't currently collapsed in this picture. Because if I add A to both sides, then I get A plus B on the left and A plus B plus C on the right. So they would need to be collapsed too. So I need to collapse this pair again. And you can easily check that this is the only non-trivial consequence. So what I've got here will be a congruence, and I get this as my quotient. So I'm explaining this just because, well, I think it's nice if you're not familiar with these things just to see these things actually happening, because this is what the algebraic machine learning corresponds to. We'll have a semilattice that will be too big for us to actually see, and we'll be constantly taking quotients. So this is the first, it's not really an innovation at all, but it's kind of an idea for encoding objects. And actually, they're calling it a semantic embedding. I'm not quite sure it is a semantic embedding in the Tarski universal algebra model theory sense, but it's certainly a way to encode things. So here, if we were interested in modeling a picture like this, well, we can imagine that we have pixels, and this is 9 by 9, so there's 81 times 2 because the pixels are black or white. So I could have 162 pixels here, possible pixels, white 1, 1, white 1, 2. So these are just the coordinates. And I can just think of this picture as corresponding to the sum of the things that were true at it. It seems pretty reasonable. Of course, you might ask, and this is the kind of thing that was confusing me when I tried to work this out. I mean, what happens if I add like a white in square 1, 1 to black? That doesn't make sense. And indeed, it doesn't make sense. So there's no picture that will have white and black in the same place, we would assume. And it doesn't really matter how we look at that, because if we're trying to classify pictures, for example, then we're not going to receive this. It's like a meaningless piece of information anyway. If you were going to be receiving that, then that's fine, but it would be handled differently. We'll see how it's handled. I don't really mind. I'll run out of time either way, but I've got some exit points. So, yeah.
But what is the intuition? Why would they use the sum instead of a product? If you want to say that these are the pixels that are taking value 1.
Yeah, I don't think it really makes much difference, to be honest, except for the fact that yeah, I don't think it really makes any difference. They actually have this is an example of where their presentation becomes a bit confusing. They have their own symbol for this. They do note it's just a sum, or at least just the. Yeah, there's no difference between joint semilattices and meet semilattices. It's just really notation. I mean, you have to think greater than or equal to instead of less than or equal to, but the whole thing would be the same if you use product, yeah. So they use like a dot with a circle around it and give it a name. I'm not quite sure the significance of why they've done that, but well, where they're heading toward is treating the things as essentially sets. And so this, in a way, is a bit like thinking of the set that consists of W11 and B11. And in that case, sum sort of makes sense, I would say. But it wouldn't really matter if you use different notation, it'd be fine. So one thing that comes out of this is that the semilattice that we're going to get when we start encoding pictures will be absolutely prodigiously huge. And this artist's impression is heavily underestimates just how big that thing would be, but it's not like the picture we're playing with. It would be absolutely huge. So you can see even for this very basic example, which is obviously a fairly boring classification task, the actual free semilattice here, so the semilattice that's generated without any restriction by those constants we introduced, the white pixels and black pixels, well, there was 162 of them. So all possible sums, if we allow 0 as the empty sum, and that's 2 to the 162 elements in this semilattice. So it's much bigger than the picture that I sketched just before. It's really big. This is just a schematic, therefore. And it turns out in LaTeX, there's a limit to how many lines you can do. It doesn't like doing more than 100 or something like this if you do like a for loop. So it's not really Turing complete. It's a very, someone gave a talk yesterday on finitists. It's very finitist. It's like 100 is its maximum. Anyway, so this is like a schematic here. So now we would be interested in adding another variable called maybe happy if we wanted to classify. And in this sense, it's a little bit like a constraint language or some sort of constraint programming idea, constraint optimization, I guess. And we would be imposing constraints. So this is how the actual training would proceed. Actually, we'll see later, it's not really how the training will proceed, but it's the naive version of it. We would be declaring that this happy element should be forced to be less than or equal to all the things we wanted to be called happy. And we could introduce lots of classifiers, whatever you want. And in fact, they've got lots of examples, which I surely won't get to, where they just solve classic constraint problems like n queens and some Hamiltonian circuits on popular databases of troublesome graphs for finding Hamiltonian circuits. And there, essentially, you just encode the entire concept of a Hamiltonian circuit here, and it will classify Hamiltonian circuits if you train it. Okay, so of course these could be more complicated pictures, and the team assure me that they're capable of working with much more complicated things than pictures like that one, but that was one I made. So they could be cats and dogs and whatever. That's my dog. Okay, so where does the duality come in? Well, we saw before this semilattice is really big. Obviously, a computer can't really work with something of that size. It's bigger than the size of the universe, probably. So this is kind of where the duality idea comes in. So this is a rather messy slide. So, and I've got lots of examples, and we'll go through what it means using our little baby semilattice. So what is a duality? It's supposed to be a dual equivalence between two categories. So in this case, it will actually be semilattices and, well, it would suffice to be finite semilattices and finite semilattices. So it'll be the same category. And we have these dual contravariant functors. What's that mean? It essentially means what the rest of the slide says. So given any thing in the first category, the dual will lie in the other category, and given anything in the other category, the dual of that will lie in the first one. But importantly, we get back to where we start if we do this twice. And the isomorphism should be by way of some natural isomorphism. It's a canonical construction. And categories are really not just about their objects, they're about their morphisms too. So the morphisms also get carried across. So a morphism from A to B in the first category will become a morphism from B to A, and so on. The dual of B to the dual of A, so in the other direction. So what's the point of all this? And the point is just that dualities provide a potentially very different perspective on the original. And that's what we're going to be using here. Now, I've drawn it upside down here just because it is a sort of a mirror type of thing. In the case of semilattices, this turns out to be unusually accurate because it is exactly just turning it upside down. But that seems to betray the true complexity of what's actually happening here. It's sort of just fortuitous that it's like that in this instance. It's not typically like that, as you'll see. So one very useful feature, and this is really critical here, is that surjection, so collapses onto homomorphisms in the first category, will become injections in the other way in the other category. And this is common to all of the basic setup that I mentioned. And that'll be very important. So what that means is taking a quotient, and we just saw how when we added on happy less than or equal to a picture, we were making collapses. That if we did have a duality, on the other side, that means we're actually taking sub-objects of the dual. And this is what makes it computationally viable. So I thought I'd go through a few well-known examples. They're, mathematical, I guess, but some of them are sort of logical lines. This one maybe not. So a very popular one in classical mathematics would be vector space duality over a finite field. And here we would construct the dual space as the vector space on the linear functionals, which are just all of the linear transformations into the base field. Now, if you have an infinite dimensional vector space, then you might want to use continuous linear functionals, otherwise you don't have a true duality. But in the finite dimensional case, this is it. And in fact, it's a good instance. It's actually very similar to semi-lattice duality, as it turns out, because the dual of a vector space is in fact of the same dimension in the finite dimensional case. So it's sort of isomorphic. So you don't actually get anything new. But that doesn't mean it's not really useful, because it's sort of a different way to do things. So here is locally compact abelian groups. And if you're working with finite abelian groups, then you don't need to care about the locally compact part. And here we have Pontryagin duality, which is another early one. And this is really was designed to be a generalization of the Fourier transform setup. So Fourier transform is sort of like a particular case of this at play. And here what we look at is we take a locally compact abelian group and we look at the continuous homomorphisms into the circle group, which could be called characters under pointwise multiplication, and that's the dual. And you just do the same thing to get back to where you started. So that's sort of more classical mathematics. This one here is a lot more logic aligned, I guess, which is stone duality for Boolean algebras, which is such a beautiful idea and extends to many more complicated cases. So here, which is quite an early one, so 1930s. Here what we do, well, there's two ways to think about this. We can take the space of ultrafilters of a Boolean algebra, so maximal filters, and we take them as the points in a topological space. Actually, that's the next slide. So maybe I'll look at this. Here, we just take all morphisms from the Boolean algebra into the two-element Boolean algebra, and we construct a topology on that. And there's no structure at all other than the topology in this case. You just get sets on the other side, but with topology. So compact, totally disconnected Hausdorff spaces I'll call Boolean spaces. So another way to think about this, and it's the more traditional way, is you take all ultrafilters, maximal filters of the Boolean algebra, and you define a topology with this subbasis. So for each point in the Boolean algebra, you look at all ultrafilters that contain it. And that defines a basis for a topology, and that's the dual space. So this is different to the previous two because the things on the dual space, which is, I guess, this side for you, are different to the things we had on the first side. It's not just that they're topological, they're not Boolean algebras, they're just sets. So we need to know how to get back again. And luckily, it's nice and easy. You just look at all of the sets that are both closed and open at the same time, the closed sets, and you get a Boolean algebra. But you can also do this by way of morphisms. It's just the Boolean algebra of all continuous maps into the discrete space on 0, 1 under pointwise Boolean operations. So now finally we get to the Hoffman-Mislov-Strauchl duality for semilattices. So here we are, on one side we have, well actually they did meet semilattices with 0, Guillermo, you'll be pleased to know, but for us we'll do joint semilattices with 0, there's no difference. And on the right hand side you actually have the same thing. If they're infinite though, you're going to need topology. But as I said, we can just look at the finite case, in which case it really is just the same thing. And how does it arise? Well, just like in the Boolean algebra case, it's just the set of all semilattice morphisms into the two-element semilattice under pointwise join. And we can also do it by way of sort of an ultrafilter-like idea. We can just take all of the prime filters, and I'll explain this in the rest of the talk under union. And we just do the same thing to get back on the other side. So this is a case where the duals are the same category essentially, other than the topological feature if you have the infinite, allowing infinite semilattices. So two takeaways from this is the one I mentioned before, that in the real world, so in the first category, taking a quotient corresponds to taking a substructure on the other side in the dual world. But a really important feature is that the dual object arises as a concrete object. So in each case, I describe the dual either by saying, we take the space of ultrafilters. So now we've got some fixed things. Our original Boolean algebra may have been completely abstract to some weird thing. But once we've got fixed that, now its ultrafilters are a family of sets. And now we're defining a topology on those things, treating them as points. It's arising in a concrete way. I mean, it's abstract in the sense, in a second degree level, because it's defined in terms of something concrete on something abstract. But it's a sort of a concrete thing. And this is very important. So this is a bit like if you have a group, an abstract group versus a permutation group. It's a very different situation. The cryptography is based around this. Concrete objects can handle things in sneaky ways. So our naive modelling of information via semilattices is as follows. So we start with a free semilattice on the constants that we decided for our things we were modelling. And we just create these successive quotients as we classify things. And for the time being, we're going to ignore negative constraints. So in the happy faces, I had a sad face. That's not going to be in our training set for happiness. We'll just ignore that. But it will play a role because we'll see that this idea is a nice idea, but fails miserably. In the dual space, though, each time we're taking a quotient, what that corresponds to is taking a sub-semilattice in the dual world, because I mentioned how surjections become injections. So each time I take a quotient here, for the dual, that corresponds to taking a sub-semilattice. And this is really handy because these semilattices are concrete semilattices. They are generated, their elements are prime filters, and the operation is union. And with an algebraic object, you only need to know generators of a concrete object in order to generate everything. And there's relatively few generators typically in this, and we can actually manage how many there are. So we only need to know the generators of these dual objects in order to know a sub-semilattice. So in particular, if I want to pass from this first one to the second one, I had some generators for the first one. I now need to find a slightly smaller set of generators. Maybe I need to get rid of one of these and replace it with something that was previously sort of a redundant element, something that was generated by this pair, but I got rid of this one, and I'm going to keep this bit. I need to update my generators. But I only need to record the generators to know everything because the operation is just union. So I can get anything I want just by finding which generators are inside it. Okay. So the trick is how do we know how to update these generators? Is it time to finish? How much time do we have? Okay. Okay, so our trick that we need to know is how to update the new generators each time we impose a constraint. So let's look at these prime filters. Fortunately, in this finite case, the prime filters in a semilattice are really easy to understand. So what I mean by a prime filter, I mean that it's an upset, so it's closed under going up in this picture, and it's also closed under the following property that if I have a sum that sits in here, then one of the contributing summands had to sit in there. And conveniently, in the finite case, these are just the complements of principal downsets. So if I take any point here, so here I've taken the point B plus C, and I've looked at its downset, then the complement of that will be a prime filter, and every prime filter arises in this way. So they're just the complement of principal downsets. In the infinite case, of course, you can get prime filters that are not complements of principal downsets. But anyway, in the finite case, it's just this. So here's another one, the principal downset of D, and we get a slightly bigger filter. But conveniently, we only need to know which generators are in these prime filters. So our generators for this semilattice were A, B, C, and D. So if I look at this prime filter that was the complement of the downset of D, I only really needed to know that it contained the elements A and B of the original generators. And then it's everything that can be written with an A or a B involved. If you have a sum in this semilattice that can be written with an A or a B, it's in this prime filter because it's above A or B. And it's a filter, so it's closed under going up. Okay, so the dual of the semilattice, as I mentioned earlier, is just you take all the prime filters and your operation is just union. It's pretty simple. Now, the fact that in the finite case, they are just the complements of principal downsets will actually be what ends up making the semilattice duality look a bit simple. It's just turning this thing upside down. Essentially, it's turning joins into meets. Now, we didn't ask that our semilattices be closed under meet, but in a finite case, a joined semilattice with 0 is always closed under taking meets as well, even if it wasn't an operation. And that's kind of what's happening. In the infinite case, because we're arriving at sort of topological objects, we'll also have limits of things involved. But anyway, so I'll go through a couple of these. So let's look at this first one. So my notation here is that chi is going to be the principal downset, and the filter it corresponds to is the complement of that. So here I'm looking at the prime filter that consists of everything that's not below A. And I'm calling that chi A, just because it's a bit hard to give it a different name. I'd have to call it chi B, C, D or something like that. Okay, so I put a 0 in here for A because A is not in that prime filter. But B, that is in the prime filter, as is C and D. And also these other elements at the top are in that prime filter. But I mentioned before, I don't really need to know them. I just need to know what generators are in the prime filter. So I've got these in boldface, if you like. Here's another one. If I look at the principal downset of A plus B, its complement is everything above C, essentially. C, D, plus these other 2 points. And so I can write that as this column vector. And you can go through and do the whole thing. And you can think of the dual as just being the bitwise sum on those columns. So you take the columns as your elements, and it's just bitwise sum. But beautifully, the original is just taking the rows and taking bitwise sum. And that's the second dual. So the dual of the dual is just what you get by looking at the rows here. And it's just, of course, what we started with. So you can see if you take A, here's A and here's B, A plus B is down here, and indeed 0 plus 1 is 1, 1 plus 1 is 1, and so on. You can check all of these. And you can also check the other way, but you'll have to remember that the notation here doesn't correspond to the operation. So A plus B is the name of the thing that's excluded. So you have to think as to how you come around for these. Anyway, if you draw this, it turns out to be just exactly the same thing upside down. And how have I labelled this? So on the right, each prime filter is being recorded by the set of generators that it contains. And then I've just ordered them just by set containment. So here, CAB here would denote all elements of S above either A or B. So just everything up here. And that's an example of a prime filter. So that's this one here. So I know it's just turned it upside down, but we do have this nice concrete representation. And just like before, where we only needed to know the generators on the left, we also really need to only know the generators on the right, which are the ones I've put in blue. We don't really care about the other ones because they're just unions of the small ones. And this is the fundamental trick for the algebraic machine learning. So the key idea is the order in the left-hand side can be understood by knowing about the right-hand side. So if I have an element on the left-hand side, so all of the elements are sums of generators. So if one sum is less than or equal to another on the left, that's the same as saying every element of the dual, the elements of the dual were prime filters. Every prime filter containing this element also contained this one. That's all that means. And because we've managed to convert our things to sets, it just means that every generator well, it suffices to look at just the generators. Every generator of the dual side that intersects non-trivially this set also intersects this one. Okay, so this is great because it tells us that we don't actually need to know anything about this semilattice on the left at all. We only ever really need to know about the generators over here. And any question we have about the object on the left can just be answered. So if I never have to know anything about the left, but if I want to know, is this sum less than or equal to this one? I just need to check if every element of my blue elements that intersects here also intersects there. And if that's true, then yes, they're related by order. And if it's not true, no, they're not. So it gives you a little handle on this giant semilattice, a small handle. So what we want to do is that each time we make a collapse, as I mentioned, what we need to be doing in the dual world is identifying a new set of generators. So we need to update our blue elements to a new one. And so the fundamental trick that they've come up with is just a way to do this. And it's not actually that hard to come up with, as the inventor will tell you. It's definitely just involves doing what we're doing now. So if we have a look at this particular case, B plus C, as we know, it involved collapsing these over here. And you can almost see how this thing would have arisen as a sub-semilattice of the original. So here are our, in the dual world, this is what we had. We had those blue points, and we need to update our new generators. So what we've imposed as our constraint was we forced B plus C to be less than or equal to B. We already had B less than or equal to B plus C. That was trivial. What we imposed in this quotient was collapsing B plus C below B. And so previously there were some prime filters that contained B plus C, but not B. And these were the things that were able to tell us that B plus C wasn't less than or equal to B. Now we want to get rid of them because they'll be telling us something that isn't true anymore. So the offending prime filters were the ones that were above C or D and the ones above A, C, and D. But I've not got that in blue because it's not really required to know because it was a join of some existing ones. And what we need to do is take those prime filters containing B and sort of amalgamate them with these bad ones. So you just take the union of this bad one with each of these things here, and you get rid of that. So the full crossing operator, as they've called it, just replaces the offending prime filters by the union of that prime filter with all the other ones. And this is the new generators. And you end up with these ones on the right here. So we just lost this one essentially in this case. And you can see that we did indeed arrive at the dual of the original object. It's time to finish. I don't know, what's a... Sorry? 15 more minutes, including questions. Okay. Oh, that's good. Okay. Okay, so there's a big problem with what we've done, but you can see how we maybe have a computationally viable way to do this because each time we have a constraint, we never write down that semi-lattice. We weren't interested in what it looked like. We just had some generators for the dual, which were a set of subsets of the original generators, and we just updated them each time. And that's all we ever record. And in the end, if we want to know if a happy face was a happy face, we just see whether happy was less than or equal to that constant, was less than or equal to this sum. But you can see what happened here is that because we only imposed those collapses, the only faces, the only pictures that will be above the word happy are exactly the ones in our training set. So this is like almost perfect overfitting, where you will have learned exactly and only the training set. So it's a useless classifier. So what one really wants is a way to generalize this. One doesn't want to know exactly the happy faces that you were given. You want to know things that are a bit like that. And this is where the secrety stuff comes in. And this is where, with modern machine learning, with neural networks, it also becomes a bit weird. It kind of works if you just sort of batch things to sort of simplify and classify, and then it somehow works if you train it for long enough and do the right tricks. And it's a bit like that in this case. It's just a very different process. So what we constructed was the freest model that was consistent with our training set, but we wanted a much bigger collapse so that other faces were also above happy. And wanted them somehow to be above happy for the right reasons and not for the wrong reasons. So we didn't want sad faces there. So thinking about what we did, in order for us to classify similar pictures, we needed to take bigger quotients than the ones we were doing in the naive approach. Bigger quotients. But bigger quotients means smaller subalgebras, which computationally is good news for us, actually. In fact, it makes a big difference. So instead of just doing our full crossing operator, which was the thing that matched exactly adding that constraint, we'll do a much more vigorous pruning. So we need to prune these atomizations. So I'm using the word atomizations. All of what I presented you is my version of how this works. Their version is by way of this thing called an atomized semilattice. And what an atomized semilattice is a semilattice along with enough generators of the duals. I mean, they have introduced an idea called atoms, which are exactly just prime filters as recorded by the generators of the original semilattice, which is how I presented it too. I just didn't call them atoms. Anyway, you need to prune these generating sets of the dual more vigorously. But of course, we had some negative constraints. And of course, this is a very simple classifying problem here, just a baby example. You would need to make sure that if you vigorously pruned, that you weren't collapsing too far to somehow classify a sad face as a happy face. So each time you take a bigger smaller subalgebra, so take a really small subalgebra, you want to make sure that you're not forcing something you didn't want to be counting as happy, as being happy. So you have to avoid that. That's just a check though. So here is the sparse crossing operator, which is really non-deterministic. So before we saw this idea, if we wanted to force S to be less or equal to T in the real world, in the knowledge space, where the things we know about, and we want to know what does that look like in this dual world, what I would prefer to call the character space. And we had this idea where we took all the prime filters containing S but not T, and then we sort of amalgamated them with the prime filters containing T and threw away the offending ones. Now what we want to do is we want to keep only some of them. So instead of putting them all of the new amalgamated ones in, we only put them in provided that at least we're making sure that each negative constraint is verified as not being classified at least once. So in our pruning process, so in our update process for the generators, we just need to make sure we can get rid of a lot more than we thought we were doing, because otherwise it looks like we're expanding the number of generators each time. We only really need to keep one for each negative constraint. So we can go through and check one of them must validate that a negative constraint was not above, and sad face was not above happy, and we just need to keep that prime filter. So that's a good question. No, because, but it's a good question. Because in practice, what happens is that if you just apply the full crossing operator, which is the one that's creating this Frias model, even just computationally, that's quite problematic, because in worst case, actually, the number of the generators could be exponential. So in practice, you want to always apply a sparse crossing, just considering any negative constraint if there is any. Because if you do this, so you're just keeping one or two of these, it's a small number, then you'll manage to be creating big collapses without exploding the number of generators. And I do have a slide. So this is getting a little bit more into the practicalities of it, which I'm less familiar with. But I do have some slides which are from one of the papers of this team that describe some of the little tricks that they've got. So they're doing things like tracking the evolution of these filters. So because the filters arise by being updated from previous ones in this process, if you have after 100 steps, you can imagine this filter may have arisen by an amalgamation of these and these and these, and you can track their evolution. And their general theme is that you keep a filter if it's not evolving. So ones that seem to be nice and stable are good ones, and ones that are rapidly changing usually will disappear as you train further anyway. So they get rid of them. But it's a very good question, and I don't really know a good enough answer other than the fact that it's a bit of both. Okay, so if we do this, if we don't replace everything, we just replace some of it, then we get a much smaller sub-simulatus than for the full crossing. And this means that in the knowledge space, with a true simulatus that was recording what we knew, that we never wrote down, that was actually being collapsed a lot further. In ways that we can't necessarily understand directly, but just whatever, it is just what it is, I guess. But importantly, all constraints, positive and negative, are still maintained. So in practice, of course, you don't have to have just positive or negative. You could be classifying, dogs, cats, zebras, all kinds of things. You just be making sure that nothing gets classified into the wrong spot. So next steps. So mathematically, this is quite exciting, I think, even just because it's a really neat idea. So there's a sort of a mixture of mathematics and, I guess, computational elements. So conveniently, I've spent quite a bit of time looking at dualities for objects, and in particular around simulatus-based algebras. So in this paper here with Brian Davey and Jane Keithley and Rashid Tulakta, we showed that you could create nice dualities over any simulatus with operators. So simulatus with operators, I mean a simulatus where has some other operations that have to be homomorphisms with respect to the simulatus operation. And on the dual side, you get a sort of a structured Boolean simulatus, although in the finite case, it would just be a structured simulatus. What does structured mean? Well, it just depends on what the operators were. So, and in fact, our proof is a sort of a theoretical one. So we never really thought about an efficient or nice duality, just that one exists. But if you do, it is, I mean, here's a good example. If you take simulatuses with automorphism, so this is a simulatus with a unary operation that has to be an automorphism. So it also comes with another unary operation that its own inverse. So this, from a machine learning perspective, could be quite nice because it gives you a way to maybe encode symmetries of objects for free, rather than having to learn them as part of the learning process. You could just build it in. And on the right, in this particular case, you just get simulators with automorphism. And in fact, the dual here arises by way of quite a natural space. It kind of starts to look a little bit more like something like Pontryagin duality. So you look at the full shift space, so just all two-way infinite binary strings with bitwise sum. That's a topological object, and you have a two-way shift, and that's sort of like the fulcrum for this. So just like the circle group was in Pontryagin duality. So there's lots of these things, and as to which ones are sort of viable for enriching this machine learning paradigm, I don't know. One very nice thing about the semilattice is that it just seems to be a sweet spot in terms of generating power. For example, those of you who know things like Birkhoff or Priestley duality, which is another one that will arise a lot in algebraic logic contexts, there you have distributive lattices on one side, and on the other side you just have ordered sets. But the problem there is that if you start with a free distributive lattice, it's very big, and the dual of that is already exponential in size, and it has no structure. It's just an ordered set. So if you want to record generators for it, you have to record all exponentially many points instantly. So while it's not out of the question, there's not a way around this. Computationally, it doesn't work initially. It's just not computationally viable as a framework for this. Whereas semilattices, it just seems to be, it kind of is the same on both sides, and it means that you can get by with this small set of generators always, and it's computationally viable. So exploring things like these, what was in this paper, to see which ones are computationally viable is very interesting. Another idea is to actually just generalize this a little bit, because you could still use just actual semilattice duality, even if you had a semilattice with operations that weren't necessarily homomorphisms. Because when you take a quotient of a semilattice-based structure, it is, amongst other things, a semilattice quotient. So provided you have a way to understand just how, so when you collapse 2 points, you were going to be collapsing more things than was required just by the semilattice part. But provided you have a way to understand which things were collapsed, you could still calculate what the semilattice dual was, and then maybe have a more advanced version of the sparse or full crossing operator. And the other idea is that even though duality seems to be the perfect framework for what they're doing, it doesn't really seem to need a proper full duality here. I'm not sure it's really important that when you take the second dual that you get back exactly what you want, provided that you have enough information on this dual side to understand to separate elements on the other side. So this also suggests that maybe duality is the nicest way to do this, but there might be other computationally viable ways that are not proper dualities, but just similar to that. So all of these things are very exciting mathematically, I think, and looking forward to working with this team. So I could stop there, I think, actually. So I do have a whole bunch of other slides which go into a little bit more detail on the actual machine learning part, but this is a good stopping point in terms of the overall framework.
Max, can you stop the recording?
No.